Good morning, students. We were getting used to the cool weather and now it's hot again. So I guess I'm okay with that. I just hope by the time the holidays get here that it will be a little cooler. After the holidays, before New Year's, I'm going to plan to visit my sister in Montana. So I know it'll be cold there, but I want to be prepared for the cold before I get there, so I won't be an ice cube. But uh, I don't know if I can depend on that. Now, what we want to do today is to actually work into some more identities that have become fairly standard in the calculus preparation. That is, we tend to focus on identities that you will need in the calculus sequence. And also, as you take more engineering classes, those of you that go the engineering route, and more physics classes, more math, computer science, there are just so many formulas to be had, so many identities. And the ones that we stress are actually the ones that you will have some use for. So you may discover other trig identities that you work with in a particular class that may just be dedicated to a certain pursuit, and that's fine too. And maybe you'll find that not all of the identities we talk about today you will use with the same degree, but you will see them. So the first thing I want to do is to share the screen and actually talk about a problem that you have in your law of cosines. Now, the reason I'm going to talk about this is because it's going to be a springboard to the addition and subtraction formulas. Now, I've gotten several emails or messages on WebAssign from students, and they ask, well, do I approximate? And I'll say, well, no, the problem doesn't list an approximation, so you have to give an exact answer. But when you actually solve it using the law of cosines, they give you a really good hint. There's one angle that you don't find on the unit circle. That is when you apply the law of cosines for one of the sides of the angles, you have an a squared, a b squared, and a c squared that you have to evaluate, then use the Pythagorean theorem. You end up with a cosine of 75 degrees. Now, the thing about that is the way the polygon is structured and broken up into triangles. You see that this is just the sum of two triangles, or two angles, excuse me, that you are familiar with, namely 30 degrees and 45 degrees. So this is why I let this problem in for the law of cosines, because if you see this, then hopefully this would prompt you to try to look ahead or think about how the cosine actually behaves with sums. Unfortunately, it's not additive in the sense that you just say cosine of 30 degrees plus cosine of 45 degrees. Functions that have that quality are few and far between. And so we don't have that luxury with the cosine function, nor do we have that with any of them actually. And so when we look at this, we're like, well, here's a question mark. So we'll just write to the side here, we need an exact value. Now, of course, you're thinking, well, you know, you could just run the problem and you could see if WebAssign would let you get away with this. That is, you just leave cosine of 75 degrees in your formula. I haven't tried that, and so most students end up asking me, and I share the idea with them. But again, you know, WebAssign is very flexible about exact responses, but they might be kind of, you know, hinging on the part that you're going to actually put down radicals and integers and ratios of those. So again, I always tell my students, as long as you enter the exact response, it may not have to look very pristine. WebAssign will still give you that green check. Well, with that as it is, let's write down a theorem that has to do with addition and subtraction. Now, One thing that I want to say about these theorems is that we will use these over and over again, and you will remember these, but some of the theorems that we get from these equations, you may or may not remember as well because we won't use them as much. And if you feel that way, don't worry about it. You put all of these on note cards so you can refresh your memory and have them accessible as you need them. So what we're going to do first is we're just going to let A and B be real numbers. I'm going to use these for the arguments so they're easy to see. X's and Y's are fine too, but I'm going to use A's and B's and reserve the X's and Y's for later stuff. So we're not going to actually prove in this order. There's going to be one proof that will take longer, and then the rest will just follow from that particular idea. So we're going to look at sine of the sum. That has the following form. That is, this is sine of A times cosine of B plus sine of B times cosine of A. So what's happening here, and the way I'm writing it, it just looks like the arguments are flipping between the two. So they're not equal, but it's easy to remember if you actually write it in this order. But whatever order you choose is completely up to you. It certainly commute, the real numbers commute, so it doesn't matter. I tend to write it this way to remember the form of it. Now, of course, if we knew this, it's easy to get this. And when we go through the justifications, I'll remind you how we do that. So if we have sine of a difference, the only thing that's going to change is the sign here. That is, we're going to get sine of A cosine B minus sine B cosine A. Okay, and now 3, I'm just going to write over here. This is actually going to be the one that we will prove, and these will follow from it. So we're going to have cosine, basically what you would use to solve this, of A plus B. So we're going to get a lot of formulas today that will allow you to substitute numbers into these arguments to get new values. So the procedure to use the identities will be easy. You just have to believe them. So this one's going to look like this. This is going to be cosine of A times cosine of B minus sine of A sine of B. So again, it's not additive. You don't just get cosine of A plus cosine of B. You get something very different from that. So that's an identity. And then 4, which will be similar to 2 with the sine, will have the cosine of a difference. So these formulas, these identities have little oddities about them. And with the difference, the minus here changes to a plus. So very, very close together. So these are not hard to commit to memory. These you'll use often enough. And then let's look at just the ones for tangent. I'm writing them down. They don't get used as much, but they do come up on occasion. So we have the tangent of the sum, and it's a little bit easier to remember. In the numerator, you actually get the sum of tangent A and tangent B. So that's easy to remember. And then in the denominator, this is the standard form. You get 1 minus the product of tangent A and tangent B. So again, the forms are chosen to make them more user-friendly. And then for 6, we just have the tangent of a difference. Use any letters you like. If you don't like the A and the B, you can use other letters. It doesn't matter. So here we're going to have the tangent A minus the tangent B. The signs will just flip again. And we'll certainly use the even and oddness of our trig functions. That's going to make our life a lot easier. And then we get 1 plus tangent A, tangent B. So we found out how even and odd is really important with the trig functions and also the inverse trig functions, those that actually fell into that category. But then we had identities that helped us to deal with negative arguments so you could do your compositions correctly. So everything we've learned thus far, we will continue to use with these new identities. So don't be afraid to apply techniques that you already know. They're still very valid and very useful. So just surge ahead as you look at these. Now, one thing I want to do here is to look at, let me sharpen this pencil, to look at a proof of number 3, but just like we do a lot of these examples and justifications, it's nice to have a unit circle to organize the work. So again, we're going to start with an A and a B. And I will start with a positive A and positive B, even though it really wouldn't matter, but it's going to make my diagram a little bit easier. And then I'm going to look at a negative A as a clockwise angle. So again, this is just going to be a way to organize thoughts. And for trig, it's very useful. Almost necessary to organize the ideas here. If I didn't draw this, it would be a little bit hard to figure out what I was doing. So let's just draw a unit circle. So we'll think about measurement along the circle itself, which will correspond directly to the angle abstraction. So we'll have, let's just get our 4 points. And go ahead and draw our circle. You draw curves like you're shading. I mean, you can't be too forthright unless you have a French curve, and so you just kind of shade and hope for the best. Sometimes you overshoot your points because you don't measure them very well, but this will be all right. So kind of oblong Charlie Brown head, but that's okay. So what I want to do is to notate the A and the B as distances along the unit circle, or angles, if you will. And we'll start off with A. Again, you can be any size you like. This is just to kind of give you a user-friendly diagram that'll make it a little bit easier to understand the logic. So by definition, if we have an angle A or we have a distance A along the unit circle, the terminal point would be cosine A, sine A. So everything of that, we're just using what we already know, and nothing about this is really very new. And then I want to measure an angle B, say right here. And again, by definition, this will be cosine B, sine B. And then to move the logic forward, I'm going to think of adding the angles A and B. So to B, I'm going to add A, which will put me about right over here, just kind of in a figurative sense, adding another angle A here. So about right there. So this gives us the sum. So let me go ahead and write this down. This will be A plus B. So this will give us the ordered pair cosine A plus B. So we just want to see what the unit circle is, as far as the picture on the unit circle, how does that look? And that'll help us to organize the congruent arcs and the congruent chords and use Euclidean distance in a way that you can actually visualize. So now, to make this argument work, utilizing what I just said, I'm going to look at the negative of A, which would be about right here. Again, my circle's not perfect, but we'll be all right. So here we have the minus a clockwise angle. And then, of course, the cosine, we'll use the evenness of the cosine of the negative A, that will absorb and give us cosine of A using the even status of the cosine. But the sine of negative A, the negative factors, because the sine function is odd. So we get the negative of sine A, again, using the arithmetic of the trig functions. We can't get away from it. And today there'll be formulas where we have pluses and minuses, and you're going to think, well, that's the pits. And I agree with you. Sometimes we can't avoid it. And that makes for a less user-friendly formula. So we're very happy when we don't have the plus and minus. So now when you look at this, you can see, and of course, let's go ahead and notate here 1, 0. We're going to use that. So if we go a distance A plus B, we have an arc right here with this corresponding chords. And then, of course, a distance A plus B would also be for this arc, where I've used the negative A here and the corresponding chord. So the congruent arcs will subtend the congruent chords. So we can go ahead and just draw these in. Let's do it. I'll just do it with the black. And so we'll have the A plus the B here. You can label all these points, but it doesn't matter. We know what the corresponding points are. And then the other one's right here, A plus B. So again, congruent arcs subtend congruent chords. So we have this chord and this chord congruent. So what we can do is look at these points and then these points and use Euclidean distance. So instead of worrying about the radicals, which really don't matter, we'll just look at the square distances. So use the square of Euclidean distance. So again, like before, we've often labeled points, but now you're fine with this. So just put a finger here and a finger here and take the difference between the x coordinates in square and the difference between the y coordinates in square. So we have cosine A plus B minus 1. And that will be squared using Euclidean distance. Now, of course, when we look at the y coordinates, the y coordinate here is 0. So we only end up squaring the sine. So sine of A plus B minus 0 is just sine A plus B quantity squared. Now we will set this equal to the square of this distance. Again, we have cosine B minus cosine A squared. So again, like here, we have a binomial. Like this proof takes longer, but it is not difficult because it mimics ideas that we have used before. So hopefully this will be very straightforward. And it's certainly the simplest way to affect the proof in a way that actually makes sense. And then for this part, we're going to do the sine B minus the sine A. So the minus minus will give us a plus. So we have sine B plus sine A. So we we get into high gear at the end of this class. We do the advanced trig, and then we do the conic sections and the series and induction. So we kind of hit the ground running for this, the home stretch of this course, which is pretty much the way any math course goes. So now let's just go ahead and square all of these and set them equal and just see what absorbs. So here we square the cosine A plus B. And then we have the product multiplied by 2. So that'll be a minus 2 cosine A plus B. And then we square the 1. And now we move to this term. Well, that's easy. We just get the square of the sine. So that wasn't too bad. Now we'll do the same for both of these terms. So let's square the binomial. So we have cosine squared with the B argument, and then the product, so with a 2, minus 2 cosine. I'll write the cosine A first, since that's alphabetical order. It doesn't matter, but I did that up here, so I'll do the same. And then we square the cosine A. And now for this term, we'll just go ahead and write it below. We get plus the square of the sine with the B argument. And now the product of these two times 2. So I'll write the A argument first. And then we square the sine A term to give us sine squared. So now what we can notice is that we get a lot of the Pythagorean identities from the fundamental identity. So the cosine squared and the sine squared with the same argument, that's 1. So that gives us a 1. And we already have a 1 here. So that will give us 1 plus 1. So equivalently, we have 2 minus, well, let me go up here. Yeah, we have 2 minus 2 cosine A plus B. So all of these are taken care of. So this looks good. Now here we can just pair things off. We have a cosine squared with the B argument and a sine squared, that's a 1. And we have the cosine squared with an A argument and a sine squared with the A argument. That's also a 1. So 1 plus 1 is 2. And then of course we get these two terms that just stand alone. So 2 cosine A cosine B plus 2 sine A sine B. So now you notice everything's got a 2 in it, but before we do that, these 2's absorb. So their history, again, all of this is symbolic computation. And then we see that, you know, pretty much everything has a 2 in it. So we absorb these 2's and then just divide everything by 2. And that gives us a minus cosine, or I could have divided by -2, but I'll do that in the next step with the -1. Will be a negative cosine A cosine B. Again, the 2 goes away, sine A sine B. But now, of course, we want just the positive, no negative. So we now can multiply by -1 and get an equivalent equation, which is the standard form of writing this. Cosine A plus B equals, so hit these both with negatives, we get cosine A cosine B minus sine A sine B. So like I say, this proof, very straightforward if we think about it in terms of the unit circle, and very straightforward algebra. But again, utilizing what we know, we didn't have to do a whole lot of sign convention except with the even and odd, but we're going to certainly use that heavily in the next few minutes. So again, we have this result And now we can work on 4, 1, and 2. And then, of course, 5 and 6 will come out pretty simply just using the definition of tangent. So, like I said before, these 4 here, I think you'll commit to memory very easily. And since they will be the groundwork for other useful identities, if you can remember 1 through 4, you can always pick up 5 and 6 when you need them, but 1 through 4 will kind of be the groundwork for all these other special identities. So 1 through 4 will not be hard to commit to memory. You can probably already think about some ways to keep track of them. So let's look at the remaining ones. So we've got, for instance, I'm just going to pull this up so you can see it right here. Let me move the cursor over. I have to be careful not to click outside of the IPEVO window, because then it drops my IPEVO window. You can see it, but I can't. And then I have to stop the share. That gets annoying. Zoom is wonderful, but I have to remember how it thinks. So if we look at this and say, well, how do we get number 4? Let's just, well, 4, right there, see that number 4? Let's just use smoke and mirrors. So what I'm going to do is I'm going to say for 4, we write that as cosine of A minus B. It's all a lot of algebra at this point. And then we just want to write the difference, so it is a sum. So we get cosine of A plus the negative B, or the additive inverse. So now what we see is that when we use this formula, we have a new B, so to speak. The B now is the additive inverse of B. And so everywhere in here, we replace B with its negative. So we have this formula, this fits this form, so now we can use the right-hand side. So by 3, that is, we've proven that by 3, we have cosine A. A is still A, and we have cosine of the additive inverse of B. Then we have minus sine of A. A is still A, and then we have sine of the additive inverse of B. So now when you look at this, you're thinking, okay, well, this is what we did on the unit circle. The cosine function is even, so the negative absorbs like we did when we had the negative A on the unit circle. So this will be cosine A, cosine B. And then of course here, the sine function is odd, so the negative factors. So the negative can come out front, but then it will absorb the negative here. So we'll have minus the negative. So this will give us a plus. So we don't, once we have 3, we don't have to work hard to get this. That's just a simple restatement of the difference here written as a sum. And then we're done. So that gives us 4 very quickly. Now, what about 1 and 2? Well, cosine and sine are cofunctions. So those will be easy too. So I'll just say using properties of sine and cosine. I mean, that's obvious, but that's what we're doing. And sometimes it's so subtle, you're thinking, well, did we do anything? Well, we certainly did. We have the arithmetic of the unit circle. And so now we want sine of A plus B. Now, we can look at the A plus B as being the single input and then use the cofunction identity, which we talked about last class. So this will be the same thing as cosine of pi over 2 minus the angle, A plus B. And of course, we always think of reference triangle because any measurement can always be put back into the first quadrant using the reference number or the reference angle. That's really the key behind the geometric interpretation of the trigonometry. The modulo 2 pi is amazing. It's really amazing how it works. And even though you think it makes it difficult, it makes it possible. we have the arithmetic of the unit circle because of the reference angle and the reference number. So now, if you like, and this is your choice, we'll just go ahead and pair the minus a with the pi over 2 so we can use the cofunction identity again. So this will be cosine of pi over 2 minus a minus b. But now, of course, if we go back up here, oh, well, I don't even have to do that. I don't even, here's our identity right here. So we have the minus identity, this equals this. So let me just kind of highlight that. So we've got this identity, number 4, but this matches 4, where the new a is pi over 2 minus a. So again, this is, let me just use another color here. This is a new a little bit more complicated, a new a. And so what's that going to do for us? So everywhere we have an a in here, we replace it with the pi over 2 minus a. So that gives us cosine pi over 2 minus a times cosine of b. The b is the same, plus sine of the new a, pi over 2 minus a times sine of b, the b being the same. Now, this is not so bad. Cosine of pi over 2 minus a, these are cofunctions. That's just sine of a, because sine and cosine are cofunctions. That's what we use to get this. So this is sine a cosine b. Now again, I'm going to write the sine b first because I've been doing that first. But the sine of pi over 2 minus a is just the cosine of a because sine and cosine are cofunctions. So we get exactly the formula number 1 here, right here, where I write it with the same sine and cosine order with the arguments interchanging. So like I said, the getting the remainder of the identities is just using what we already know. We don't have to invent anything new, or we don't have to look into any proof that's going to be too complicated. We use what we already know to be true. So we use old identities to prove new identities. And then, of course, once we start using the new identities, they become old, you know, when we produce more. So old, new, whatever you want to call it. So now, of course, to get 2, we'll use the same technique we used here. I want to go through this because these techniques are important and they're going to help you as you do your arithmetic examples. So how you write things is going to be imperative here. So now for the difference, we're going to do just like what we did up here. We're going to write this as a sum. So a plus the additive inverse of b. So now, again, we're going to replace the b in here with the negative of b. So we see that this now fits this. And this is the truth here. So again, the b's get replaced with the negative b. So let's run it through here. So this gives us sine a cosine of the additive inverse of b plus sine, and the new b, replace b with the negative of b times the cosine of a. But of course, cosine is even, so it absorbs the negative. So we get sine a cosine b. And then, of course, sine is odd, so the negative factors. So we get minus sine b cosine a. So that was like no work at all. But what I'm trying to impress upon you is that we keep using the same arithmetic over and over. So when we start solving more elaborate equations, like you did in 6.4, we'll still use the same arithmetic, but the identities are going to help us. Some of these new identities will help us to rewrite equations. So we just have one trig term and we can treat it like an algebraic equation in cosine or an algebraic equation in sine, just like we would have like an equation in e to the x or an equation in 1 over x. So all the techniques that we've been using without even thinking about them will apply to this. So the techniques have not changed. The objects, however, have. So that's why we're trying to make this a little bit more understandable. So when we start using the equations, we'll have some tools to work with. Now, let's just go ahead and finish off the tangent one so you'll see how to do that. So for the tangent, that was number 5. We have tangent. This one takes a little bit more time, but of course 6 will be just like this one, and so that won't take any time. Now, what's tangent of a plus b? Well, since we know a whole lot about the addition formulas for sine and cosine, let's just go ahead and write this by definition. This will just be sine of a plus b divided by cosine of a plus b. So again, we want to use the fact that we understand the addition formulas for sine and cosine. So let's just use that. Let's not reinvent ourselves. And so now we'll just go ahead and write out what these are. So this is like doing an identity exercise. We're actually proving the identities I've written down. I mean, we're doing that. I mean, that's what we're doing. So we're doing 7.1 and 7.2 and 7.3, and we do identities. We do exactly this. And so now what is sine of a plus b? This is sine a cosine b plus sine b cosine a. And what's cosine of a plus b? Well, we proved that too. That's cosine. That was the difficult one. Cosine a cosine b minus sine a sine b. Now, again, you might be thinking that, okay, well, this is true. This is true. Why don't we just stop here? You know, that's true. We know this is true. Well, what we found is that the standard formula is written in terms of tangent. Maybe that makes it more user-friendly. Not to say that this is bad, but there's a whole lot of different functions running around, namely sines and cosines. So maybe we can bring everything together in terms of one. So one trick that we can use is thinking about where we need to go is maybe multiply and divide by the reciprocal of this term. So that's what we're going to do. Again, an identity is an equation that is true for all values of the variables for which it is defined. So we don't care about when it's undefined. That doesn't exist anyway. So don't have to worry about that. Just like with the logarithms. I always have students, well, how can we do this? I said, well, it's an identity. So if it's different when you do it that way, then the identities are no good. Oh, I see, Professor Ron. Well, see, that's just it. If you don't believe these, then you can't move forward in the problem. You have to believe them. And once we prove them, then we're done. And we accept them, you know, as any valid mathematical argument. And if it helps us get where we want to go, then even better. So now what we want to do is just go ahead and multiply. So just think of these as parentheses. So we have sine A cosine B divided by cosine A cosine B plus sine B cosine A divided by cosine A cosine B. And then downstairs, we'll just do the same thing. Cosine A cosine B divided by cosine A cosine B minus sine A sine B divided by cosine A cosine B. So now what we can do is notice that the cosine B's absorbed, and here the cosine A's absorbed. So that really simplifies the numerator and gives us, again, a tan A and a tangent B, which is what we wanted. So that's a technique we've used before, and you'll certainly use again, uh, a convenient one, so to speak. And now, of course, this is just one because we're dividing by the same thing, numerator divided by denominator equal. So that's a one. And then, of course, here we have tan A and we have tan B. Not that they absorb, I'm just highlighting the fact that they give us the product of tan A and tan B. So that was fairly straightforward. So we can look at this as maybe a problem like we did last week. This would be a problem like we did last week if we knew, you know, the basic identity. Once we know the identity for cosine here, then we can do this. So really what we think about is once we get the ball rolling and we get a new idea, we spend a little more time with that, and then the new idea will give us a lot of other identities that we get for much less effort. So that's basically how math runs. I mean, that you prove a difficult result like the fundamental theorem of calculus, and then you have all kinds of things that flow from that. So we pay our dues to be able to have better problem solving skills. Now, for the last part, what about tangent of A minus B? Well, we do the same thing we've done before, and this is a common technique that you'll have to use. That's why I'm doing it. You know, you might write 3x as x plus 2x. I mean, you do something that simple, it pushes the problem forward. It makes one argument into a sum of arguments. It makes one argument into a difference of arguments. And then you can use the sum or addition formula or the subtraction or difference formula. So the idea is that the common use of algebra moves the trigonometry forward. So now let's write this as a sum. So we get A plus the additive inverse of B. So now we have this formula. So we just sub here and we've got a new B. So everywhere we see a B, we replace it with its additive inverse. So we get tan A plus tan of the additive inverse of B. And then we get 1, that's fixed. And then we get tan A. And then we get tan times the additive inverse of B, or the negative B. But now you already know the tangent is an odd function, so the negative factors. So we get tan A minus tan B. And then, of course, the 1 is fixed, but now the tan, we've seen this before, the tangent is odd, and therefore the negative factors, and then we have the minus minus. So that'll give us a plus. So we have 1 plus tan A, tan B. Now, the idea is that we don't get as much use out of 5 and 6. They don't come up as often because the calculus of the tangent function, it doesn't complement like the sine and cosines do. So we don't have as much use for this, but that's okay. I mean, it doesn't mean that this is a waste of time. It's just that the sines and the cosines, because of their complementary calculus, makes the use of these formulas indispensable. Okay, so good for us that we've got these. Now, what I want to do, and we'll come back to these formulas, we'll certainly need to use them. So let's go, before we do some examples here of other things, I want to just now say, okay, well, how did we begin this conversation? We had that problem that you're doing in section 6 that looked like this. So we have cosine of 75 degrees. So I want to do this first before I do another lemma, do a couple of exercises with that. And then I want to go back to how we can use our newfound friends to get some even better identities that we will have great use for. So now, just like we had before, we'll say, okay, well, I need an exact value. So I'm going to do what Professor Ryan recommended we do, which is really what the picture in the WebAssign told you to do is write the 75 as the sum of two angles from the unit circle. And now we have the formula from our identity theorem. So this will be cosine of 30 degrees, cosine 45 degrees. And then of course, now we have the sum, so we get the minus here. So we have sine of 30 degrees and sine of 45 degrees. Now, this is good because we know all of these. And for this problem, this is imperative. You have to have this because the decimal approximation is not allowed. And this is better anyway. So now we just fill everything in. Cosine of square root, excuse me, give you the answer. Cosine of 30 degrees, that'll be square root 3 over 2. The cosine of 45, 1 over root 2. The sine of 30 degrees is 1/2, the terminal point, again, our friend. And then, of course, the sine of 45 degrees is 1 over root 2. But again, WebAssign doesn't really care. I want to do a little bit of work with this just to practice again with the radicals. Just remember, when you're running out of time on WebAssign and you don't, have to worry about anything but an exact answer, then type it exact and go. Okay, you don't have to make it look beautiful and pristine because there are no formatting issues for that. WebAssign never says, make sure there's no radical in the denominator. You have never seen that. You never will see that. So if you come to grief, it's because you're wishing for things to be there that aren't. So don't do that. So now we have 2 root 2, and then we have square root 3 minus 1. And you're thinking, okay, that's fine. Now, if I want to do, and I'm thinking when I've helped students with this example, I've said, just leave it this way. And then when you use your law of cosines, you can absorb the 2 and the root 2 into the factors that you have multiplying this term. So now what we're saying is that in order to sometimes push a problem into the exact realm, we have to use ideas we already know, but we have to figure out how they're connected. And once we figure out this connection, then we have a way to solve this. So I've enjoyed getting the messages here because students will say, well, I think I worked this right, but I'm not, and then the comment is like, it doesn't say approximate, and I did, so what do I do? And I said, well, look forward to the addition formula and see what it'll give you. And it's amazing how many students have figured this out. So again, this is again a new idea from old ideas. So we haven't really learned anything new except how to combine a argument of a sum with a cosine function, and with a sine function, and with a tangent function. Now, that's all and good. There's one other result in this particular section that I find to be very useful that you will use in physics, more mathematics, and in engineering. It'll be a way to combine 2 trig terms into one term so you can use your transformation techniques to graph it, like we learned in chapter 5. So here's a lemma. The first time I actually saw this was not in a trig class at Carolina. It was in an engineering math class where we were studying differential equations. And I thought, okay. And so when I saw this in Dr. Stewart's book, I thought, well, good, let's go ahead and let the cat out of the bag early. And this will be something that you can use in the future. So what we want to do is fix A and B in the real numbers. And I'll just let X be real. This can be variable. So here's what the lemma looks like. We have A times sine X plus B times cosine X. So maybe you need to think about this in terms of a graph, but it's a little bit uncomfortable because we've got a sum. Sums are difficult to graph, especially with trig functions. But if we can combine them, then we can use what we've already learned. And there is a combination. It looks like this. We get Pythagorean. That is, we get the square root of a squared plus b squared times the sine of the addition argument. That is x plus 5, where tangent, this will remind you of a triangle, tangent phi is actually b over a. So what we see here is that we have a formula that is based upon an addition formula. And so this can be of use to you. Now again, maybe you solve the differential equation and you see that. And you're thinking, well, I have this. Are these equal? Are they equivalent? Okay, well, then you'd have to do some work to figure that out. But how nice it would be that you would already be familiar with this. So how would you go about justifying this? Well, it's very simple. We're going to think of this in terms of how we think of triangles. So what we can do is define, if that's the definition of tangent phi, let's define sine phi to be b over the square root, thinking of a right triangle. And let's define cosine phi to be a, again, thinking like a right triangle. Again, the reference triangle is the key to these types of problems, because the sides of a triangle are non-negative. So you have to think about the arithmetic as which particular sign do you attach to the x? Which sign do you attach to the y? Well, it depends on where the angle terminates. What quadrant are you in? So again, the arithmetic is the same as we've always done. So now, what does this mean? Equivalently, b is just the square root of a squared plus b squared times sine phi. And a is just the square root of a squared plus b squared times cosine phi. So these are a little bit more complicated equations, but what we get when we do trigonometry. So now we can add them. Then a sine x plus b cosine x. Let's just fill everything in. Square root a squared plus b squared times cosine phi times sine x plus square root a squared plus b squared, again, b sine phi times cosine x. But now, of course, we can factor the square root. And I'll just go ahead and write the sine x first, because that's how I write the identity. So we'll do the sine x times the cosine phi plus the sine phi times the cosine x. But that's just the addition formula that we proved. So the theorems go both ways. That's where you do the log identities, and you have to think, well, do I need to combine or expand? Do I need to compress or write several terms? We do the same here. So now we want to, I guess, think of compressing. So this will just be the square root of a squared plus b squared, and then we get sine of x plus 5. And obviously the definition here gives us that, so we're done. So we kind of said, okay, well, if that's the truth, then that must be the truth. And this implies that, so we're done. So the thing about math is that you've got to lead your argument in a way that gets you to the finish line. So don't ignore the obvious. That's what you have to do. That's what any math problem requires. So again, The WebAssign will have a few examples where you'll have these, and then you'll get your A and your B, and you'll figure out your phi if it's a good number. Otherwise, you'll just write, inverse tangent of B over A and put that in for phi, and you're done. I mean, it doesn't matter. Usually what WebAssign tries to do is give you a B and an A that give you something on the unit circle, so you get a nice number or whatever, but it doesn't matter. You know what to do. You know how to work with inverse trig functions. I've taught you about that, maybe more than you wanted to know. Okay, now let's just look at a couple of examples before we get to some of the new identities. I've got a couple of examples here that use some of our newfound friends, just in arithmetic examples. Again, keep using everything you already know. Nothing is outdated. Everything is good. So any technique you've learned before, keep applying it. If you have a new identity, you can still apply the same technique. So here's an example. What we want to do is compute, in this case, compute the exact value. So WebAssign will say, compute this. So this will just give us some practice with these identities. And then, of course, in the next section, as I derive a bunch of new ones, you'll do the same thing. And you have to spend some time on reworking these and deriving these identities to get comfortable with them. If you just stare at them, they're going to, make you come to grief. So write them down and get used to them. Now, when we compute this, we want this to be exact. But the first thing we notice is that tangent is odd. So this negative is something we don't have to worry about. We can just go ahead and factor it. So we have the negative of tangent of 5 pi over 12. And so the idea is we want to be able to write this in a way that will allow us to use what we already know. And then, of course, that just says, write the 5 as a 2 plus a 3, and then multiply it out. So we get what? 2 pi over 12 plus 3 pi over 12. I mean, if we're going to find an exact value, we can't use our Google approximation because that's not exact. I mean, it's a great approximation. We kudos to our Google calculator. It's a wonderful tool, but that's not what we need in this problem. So now we're thinking, okay, this is going in the right direction, so we can reduce these, and then we will see that we have nice unit circle angles, namely the 2's absorb, we get pi over 6, and here the 3's absorb, and we get pi over 4. So now we have the sum formula for tangent, and all we have to do is fill in the A and the B. So you can think, I mean, you don't have to, whatever letters I've used, you can use your own, but I'm using A and B. Later, I'm going to use an alpha and a beta, but this is simple. And so now we can just now substitute this into our sum formula for tangent, remembering the negative on the outside. So we have tangent of pi over 6 plus tangent of pi over 4. I mean, this is just straightforward substitution, nothing too complicated here. And then 1 minus tangent pi over 6. Juxtapose, I put a little dot there to remind you what you're doing. Tangent of pi over 4. So now, of course, the tangent of pi over 6, that's 1/2 divided by the square root of 3 over 2. So the 2's go away, and we just get 1 over root 3. And then, of course, tangent of pi over 4, the sine and cosine are equal, so we just get 1. And then, of course, downstairs, 1 is fine. And here we just get, again, the same thing, 1 over root 3 times 1. So this is minus 1 over root 3. Now, if you like, you can just go ahead and get a common denominator here and absorb the root 3's. So we'll have 1 plus root 3 divided by root 3. And here we have root 3 minus 1 divided by root 3. But now, of course, the root 3's absorb, and that will give us the negative of 1 plus root 3. You're thinking, well, I could stop anytime. WebAssign wouldn't have a problem with this. And then I've got root 3 minus 1. The root 3 is going away. And then if you wanted to run the negative in downstairs, you could say, well, you know, really, let me just make a comment here after I write this. You could stop here, but that's a lot to type. This is less typing, and certainly this is fine. I mean, there's no requirement to do anything but type an exact answer. So again, once you kind of remove yourself from the tangents, the WebAssign's probably looking for, you know, no actual trig functions, but this would certainly be correct. That would be unfortunate to type, but correct. That's correct. That's correct. Now, if you just have plenty of time and you know you're doing homework and you just want to say, well, let me just rationalize. Just maybe I'm doing a rationalizing problem, just a useless little example that not getting me anywhere. But you're thinking, okay, I could just multiply by the conjugate of the denominator. So let's just do that just to remind ourselves that we can do it. I thought about this because I've done this before. And so we just think of what? Distributing. But now, of course, again, not required, just practice. We just square this, so that would be 1 plus 2 root 3. Square the root 3, that's just a 3. And then, of course, downstairs, we have a difference of 2 squares. So that's 1 minus 3. So we have 1 plus 3, which is 4, plus 2 times root 3, divided by negative 2. So then you can just divide everything by negative 2 and get negative 2 minus the square root of 3. Now that's nice and neat, and that's certainly equivalent to this, all of them being equivalent. But again, just as practice. But again, when you're working your problems, and especially I've noticed when students are working triangle problems, it doesn't matter if you have, you know, negative 3 divided by the square root of 13. I mean, there's nothing wrong with that. That's fine. That gets you where you want to go and on to the next problem. So if you have extra time and you just are interested in making sure that maybe your answer corresponds to what your physics professor got or your engineering professor got, do the conjugate method and verify that. So again, just remember, only do extra if you want. WebAssign does not require it. Exact is exact. Exact, 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 etc. Now, the other example that I wanted to do actually involves the cosine, just to give us some practice with that. Because we've used the sine a lot, we've used the tangent, so let's use the cosine and look at just an example. Now, of course, you can do algebraic expressions just like we did before, same technique for the inverse trig function, so dive right into that. So example, we want to compute, this will just remind us of our triangles, because we like the triangles, they're very useful. We want to compute cosine of the difference, and we're given that cosine of theta is 5 over 13, and theta terminates in the 4th quadrant. Okay, that's consistent. We know cosine is positive there because x is positive, but now we just say x is positive, y is negative. So that's the arithmetic that we have to use for this quadrant. And then we're given some information about phi. Tangent of phi is, in this case, the negative square root of 15, and phi terminates in the 2nd quadrant. So of course, this is consistent there because we know x is negative and y is positive. So this is the arithmetic of the quadrants. So when you think about solving this problem, we know the difference formula, so we're just going to have to fill it in. So what we do is draw our reference triangles and then affix the proper sign for whatever trig function we need and fill it into the formula. So just like we've done before, use triangles when it helps you move the problem forward. Triangles are simple, easy to use. So now notice we have what? Adjacent over hypotenuse. So the ratios are really nice. So we'll put our theta here. So adjacent, hypotenuse, and of course these look, that's a Pythagorean triple. So we get what? 13 squared is 169 minus the 5 squared, which is 25. So that gives us, right, that'll give us a 4 and a 4 and a 1. And of course that's 12 squared, right? So that's a Pythagorean triple right there. So that was easy. Now, here we think of, again, the reference triangle. Let's just think of reference triangle without the sign. Reference triangle. We would have tangent of phi would be root 15 over 1, thinking about the reference triangle in the first quadrant. So let's draw it. Again, remembering that x is negative and y is positive. So we have phi here, and then we have opposite over adjacent. So we get the square root of 15 opposite over adjacent. And then now we can get the hypotenuse, just square this. So that gives us 15 plus the square of 1, which is 1. So that's 16, which is 4 squared. So again, we have a very simple triangle here. So if you write this first, just like if you were doing inverse trig problems with an algebraic expression, this will simplify the work with the trig functions. And again, of course, obeying the arithmetic of the quadrant where these actual angles terminate. That's very important. So now let's just write down what this is. Cosine of theta minus phi. That's just our difference formula. Let's write it down. We get cosine theta cosine phi plus sine theta sine phi. So now we can go to the triangles. Now cosine theta, well, we already know that. That was given. So that's 5 over 13. Very simple at this point. Now we need cosine phi, but of course we're going to have to affix the negative sign because we're in the second quadrant. So we have adjacent over hypotenuse. So that would be a negative 1/4. Now sine theta, again, we're in the fourth quadrant, so we're going to need to affix a negative sign. So we do opposite over hypotenuse. So that will be a negative 12 over 13. And then sine phi, again, phi here, we have that y is positive. So we need opposite over hypotenuse. So that will be square root of 15 over 4. Now, I mean, you know, that's nice and exact, no problem with that. But usually you might want to reduce it a little bit to cut down on the amount of clicking with the keys. So this would just be what for playing cards, 4 times 13, that's a 52. And then, of course, we get a negative 5. And then a negative 12 times a square root of 15. So that would be an exact. So the key here is it really depends what the problem gives you. These are not angles on the unit circle, clearly. But depending on what the problem is asking you to do, if you have this information, you can get an exact answer here. So the data that you have will often come in different packages. And so you don't worry so much about anything except making sure that you have the best possible exact mathematics, the exact computation that gives you something to work with. And so if you need to get a Google calculus approximation using your Google calculator, you have something very good to start with. We have to cut down the variables as we work through the problem and make sure that each step is what we want it to be. Okay, so we're thinking, all right, we have all these nice formulas. We see the arithmetic, which is just like what we've been doing. So what else can we get out of this? I want to say now that we're going to develop some identities that you will use and you will come to enjoy and put in your memory bank and carry with you for the rest of your education. And then, of course, as you get older, someone may ask you, once you're an engineer or or a professor of physics or mathematics or a computer analyst, they say, oh, do you remember trig? And instead of saying like, well, I've forgotten that, say, well, no, I have Professor Ron, he beat this in my head. So let me help you with this. And then you'll be the most famous person in the world. You'll be that student's hero that you help them with their trigonometry. So learn this and keep this in your brain so that you can be a mentor to someone who will be in the same path as you are now. They'll be struggling with their trig, and you encourage them to keep the good fight and finish the game, so to speak. So let's get some new identities. So this will be 7.3, new identities. So what we're going to do is we're going to basically just take what we already know, these sum and addition formulas, and rework them. So first, we're going to start out with the double angle. These are easy. So I want you to put these on note cards, double angle. So what does that mean? That means we're going to replace the B with the same letter. So here we're going to say we start out with sine, and instead of writing B, we just write another A. So now we have sine of the double angle, sine of 2A. Of course, when I do the 2A, I just don't usually use the parentheses. Of course, WebAssign makes you use the parentheses. So we have sine of 2A. Well, now you're thinking, what's that equal? Well, we just replace B with A. So we get sine A cosine A. There's nothing to interchange now, plus sine A cosine A. Wow, okay. So we get two copies of the same term. So this is just 2 sine A cosine A, the double angle. Very, very useful formula. This will come up quite a bit in your work. Sine of the double angle. So there's a new one right there. So really, we just have to remember 1 through 4 from the first page. 1 through 4, we're in good shape. Let's do the same for cosine. We'll do that for tangent. Tangent's not big deal, but we'll write it down anyway. So let's do cosine of A plus A. That is, let's replace the B with an A. So we get cosine of the double angle. So now we just write it down. So this is going to be cosine A times cosine A minus sine A times sine A. You can use any letter you like. You can use a U, theta, whatever. But now we just get the difference of two squares. This almost looks like the Pythagorean identity, but not quite. It's more like the hyperbolic functions. So we get cosine squared minus sine squared. So you're thinking, okay, that can't be all, and it's not. Here's one form right here. And then another form that's gained, there are two more forms that have become very popular in the calculus. And that is, let's replace cosine squared with 1 minus sine squared. So 1 minus sine squared minus sine squared. So that gives us 1 minus 2 sine squared. So now we have another form. Maybe it's more convenient to write the cosine of the double angle with the sine function. Maybe it's okay to leave it like that. Well, the other case would be like just replace sine squared with 1 minus cosine squared. What do we get with that? So if we distribute the negative, we get 2 copies of cosine squared. So there's another version. All of these versions get pretty much equal play. Again, we don't have that here because we just got a simpler function, but here we've got this difference of two squares. So we found all three of these to be extremely useful, and you will find uses for them, okay? So put these on a note card, memory bank. Now, what about tangent? So we'll just call this 1, 2, and 3. So let's do tangent. What if we replace A or B with A, we get tangent of the double angle. So again, let's fill it in. So we get tan A plus tan A, that is we replace B with A, and then we get 1 minus tan A times tan A. So this one, not very useful, but when we get to the half angle formula for tangent, it'll reign supreme, and so it'll have a comeback. So now we have 2 tangent A divided by 1 minus tangent squared. So with this one, not as much use, but still useful, depending, maybe you're doing a physics problem that can use this. Now, the double angles became famous with this and these two guys right here. These are what give rise to what we call the power reducing identities. And they are, again, of really, really high importance. So we're going to look at these two guys. So the next thing will be power reducing. When we say power reducing, we just mean that we can take the square to the single power. Right now, you just have a buzz phrase to remember them. Okay, so what we're going to do is like, all right, so let's just write this down. What if we needed an expression for sine squared? What would that be? We want to reduce the power of sine to a first degree power of something. And what about reducing the square of the cosine to a single power? What do we do? Oh, we just go right up here. So now we'll just solve, we'll take this, this equation, cosine 2a equals 1 minus 2 sine squared a. And we're thinking, okay, well, okay, good. We can solve for sine squared and write it as the first power of cosine. So take the sine squared over and take the cosine of the double angle over. And now divide what? Divide by 2. Oh, sorry. I need my 2 there. That's like critical, need the double angle. The math does not let you make mistakes. If you let the math control you, then that's not good. The math tells you what to do and you work with it. Don't be controlled by it. Work together. And don't make it up. So we're thinking, look at that. We can replace sine squared a with 1 minus cosine of the double angle divided by 2, where the power of the cosine double angle is 1. So we went from power 2 to power 1. Learn this. Very important. Extremely important. For integration, it's indispensable. Or you can use the reduction formulas with integration by parts, but again, that's another formula to memorize. What about this one? Let's go right here, excuse me. Cosine of the double angle equals 2 cosine squared a minus 1. Well, let's just take that over. So 2 cosine squared a equals 1 plus cosine 2a. Again, the 1 joins the cosine 2a, so we get 1 plus cosine 2a. Again, we see the difference between the minus and the plus, and when we divide by 2, the square of the cosine is 1 plus cosine 2a divided by 2. So now, and this is very important, ladies and gentlemen, this is cosine squared equals 1 plus cosine 2a. So this is a single angle. This is the double angle, okay? So the main thing here is that we have formulas that reduce the power of the sine and the cosine. Now, we can't be picky, but you might think, is this any good? Well, I'm here to tell you it's very good. It gives you many good uses in the calculus. And also in, not so much in solving equations as much, but definitely in doing trig integrals and in Fourier analysis. All of this you will see if you become a double E major in engineering. You'll see all of this again and live this stuff. And all the nice integrals and Fourier series that you'll have to work on. So very nice. There's some great cheap Dober books on Fourier analysis if you ever want to invest in those. They don't cost anything. They're pennies on the dollar. Now, so power reducing, big deal. Now what we want to do is say, okay, if we have power reducing, what about half angle? What if we cut the angle in half? We double the angle and we use the double angle to get the power reducing. What happens if we cut the angle in half? Well, let's just use these right here. So let's use these. So let's call this half angle. Now, are these useful? For arithmetic calculations, they're useful. Not so much with the calculus, but you never know when you're going to use something. Now, the double angle, not so great for the unit circle. We can double angles, we just get another angle on the unit circle. But halving the angle, like going from 30 to what, 15, or 45 to 45 and a half in terms of degrees, that's useful. That gives us another exact value that we may need in a trig problem or a physics problem. So half angle, what we want to do is take this, replace A with A over 2. The half angle, double angle, half angle. Common sense, right? And it's uncommon, right? Common sense is not common. We should call it uncommon sense. So we have sine squared of A over 2 equals 1 minus cosine A. So we replace A with A over 2, so it absorbs the 2, divide by 2. Now let's take the square root principle, plus or minus. So this is not very user-friendly. So sine of the half angle, again, we have to determine where the A over 2 terminates, will be what? Plus or minus the square root of 1 minus cosine A divided by 2. And most students say, oh man, I don't like this formula. Got to work too hard, too much arithmetic. Well, that's just the way it is. Nothing very elegant here, but just square root properties. So we're thinking, all right, well, we'll take it. It's better than what we had before. And again, how do you choose the sign? You figure out where A of 2 terminates. Now let's do the same for the half angle for cosine, and we'll just replace A with A over 2. So cosine squared, A over 2 equals 1 plus cosine, again, 2 times A over 2. That'll give us A divided by 2, square root property. Cosine of the half angle will be plus or minus the square root of 1 plus cosine A over 2. Again, not the best. We have to again figure out where A over 2 terminates, and that will allow us to choose the sign. And so you're thinking, oh man, this is not the best. What can I do? What can we do with situations like this when we actually need maybe, let's just ask this question. Is it possible to come up with a formula for the half angle of tangent that doesn't have all this plus and minus. And you might say, well, no, we'll just take the ratio of these two, Professor Ron, and the twos go away and we get the plus or minus radical of 1 minus cosine A over 1 plus cosine A. Well, ladies and gentlemen, if that's all we can do, why bother? I mean, we've done this before. I mean, it's like, so what? It's not an improvement, but I'm here to tell you there is an improvement. That is, we're going to say remarkable formula. What do we say about remarkable? When you say someone is remarkable, I say you are remarkable because you make a difference. Because you do what you do and you make a difference with integrity. Well, when I call a formula remarkable, I'm saying, look at what we can get, this magnificent formula with no plus or minus that does all the work for us. So we're going to call, like we call a person remarkable, we're going to call this a remarkable formula. So what is it? It looks like this, and you can conjugate this if you want, but I'm going to do the tangent of the half angle. And this equals the following. That is, this is sine of A divided by 1 plus cosine A. There is no plus or minus in this formula. That is a remarkable formula. You can multiply and divide by 1 minus cosine A and flip it around, feel free. This is basically the theory behind the Weierstrass substitution for ratio for rational expressions of sine and cosine in integral problems. This is a non-trivial substitution that allows you to deal with those. Computer algebra systems knock this out, but when you do it by hand, it is quite a bit of work. Not all integrals that are rational in sine and cosine require it, but it is truly a remarkable formula. Did we just make it up? I don't think so. So what I'm going to do is show you some uses of the double angle formula where we have things again. So watch this. Observe. We can do sine. Think of sine as a double angle. What's half of A over 2? So this will equal 2 times sine of A over 2 cosine A over 2. So basically, we're just taking the double angle formula. Instead of starting with 2A and having sine A cosine A, we start with A and just half these. So this is equivalent, kind of like we did up here at the top, right here. So we're thinking, all right, well, can we do the same with the cosine? Absolutely. So what we're going to do, we're going to use, let's see, what did I do with it? Yeah, we're going to use this one. We're going to use this one and do the same thing. We're going to start with A, in this particular case, A instead of 2A, and then cut this down to A over 2. So let's do it. So we'll say cosine of A equals cosine squared A over 2, and we got a 2 there, sorry, 2 minus a 1. So again, this is imitating this guy right here. But now the A has become A over 2, this guy right here. So when you look at this, you're thinking, oh, I see it, Professor Ron. Add 1 to both sides. So we have 2 cosine squared A over 2 equals 1 plus cosine A. So you're telling me that that's tangent of the half angle. Well, let's just compare. Let's just see. Then sine A, this is like starting with this and proving it going in this direction. So we're improving an identity. So we have sine A divided by 1 plus cosine A. Well, let's write it down. that equals this, 2 sine of the half angle, cosine of the half angle. And now we can write the square as a product of two singletons. So we get 2 cosine A over 2 cosine A over 2. And now these absorb. And the 2's absorb. And we're left with sine over cosine, which is tangent of A over 2. You should know this. You need to know this, but you should know what I've done here. This is a remarkable proof and a remarkable formula. I didn't learn about this formula until I took Calculus 2 as an undergraduate. It was in the Swarkowski book. I was amazed by it. The idea is that they used to just reserve this for the calculus sequence. Now, Dr. Stewart is trying to push it into the pre-cal, so when you get to it, you're like, oh, I've seen this before. This is not so bad. So having had some practice with something before you use it, just like learning some calculus before you take physics, there's a reason behind that. It makes you better. So here we have it. In your brain, put these on note cards, okay? Know how to do this. This is a nice proof technique, taking everything backwards. Sometimes you think about where you need to go and then you rearrange things to get you to that finish line. Now, what we want to do is take some of the formulas that we have already and mix and match. So we're going to go back to the formulas we've been working with and do what we call in the literature product to sum. Product to sum. And you'll get some good use of these in your WebAssign. So what you need to do is have all these written on note cards or use the formula sheets on Blackboard and have them ready to go as you work the problems. Because you're going to, if you want to have to rederive every time you work with them, I don't want you to do that, but I want you to write down enough so that you feel confident. So let's just get the product to sum. So we want a product to equal a sum of trig functions. So we'll start with these two. Actually, four, the primary one, sine of A plus B equals sine A cosine B plus sine B cosine A. Write down number 2, sine of A minus B equals sine A cosine B minus sine B cosine A. Now we'll do the cosine ones. Cosine A plus B. Sorry, let me get a little more focus. So we have cosine A plus B, cosine A, cosine B minus sine A, sine B. Remember, that was the first one we proved. And then number 4, we have cosine A minus B equals cosine A, cosine B plus sine A, sine B. Now, like I said before, to get the product to sum, all you need to know is these. If you know these, you can derive them on site and not have to worry about memorizing anything. Just know these formulas and you're good. So for the first one, we're going to add 1 and 2. So when we add them, notice these terms absorb. They're the same. So we get 2 times sine A cosine B equals sine of A plus B plus sine of A minus B. And then divide by 2. So the product, sine A cosine B equals 1/2 sine A plus B plus sine A minus B. So you're thinking, why do we care? Well, very useful with integration. Again, this would require integration by parts. We can do very simple integrals here. So this is very useful in Fourier analysis, very useful in calculus 2. All of these are useful in calculus. That goes without saying. Now, what if we want these to flip around? Okay, let's not do any more adding. Let's just flip them around. So 2, let's do the cosine A sine B. So we'll do sine B cosine A, and then we'll flip the final product. So the A and the B interchange. So we just have sine of B plus A, which is A plus B. That's not going to be any different. And then we have sine of B minus A. Okay, well, what is that? Well, that's going to be 1/2 sine, and let's see here, 1/2 sine of A plus B. And then, of course, we're going to factor the negative here and factor the negative. So this is going to be sine of A minus B. So now when we write this as the negative of A minus B, the negative factors out here because the sign is odd. So now we get cosine. I'll do the cosine first. You're thinking this is redundant. We don't even need this problem. But the books like to write it down, and it's helpful for the sum to product. So this gives us 1/2 sine A plus B minus sine A minus B. So again, a companion formula that you can get just by interchanging A and B. So really, if you know this, you automatically know that one. But it's convenient just to have it written down, and the literature always includes it. So we'll just do the same. Now, for the next one, for 3, we'll do what we did up here. We're going to add 3 and 4, and then subtract them because we don't have the luxury of the sine cosine terms here. So add 3 and 4. So now notice these will absorb, and we're left with 2 copies of these. So we have 2 cosine A cosine B equals cosine A plus B plus cosine A minus B. Now divide by 2. So cosine, the product of 2 cosines with possibly varying arguments, will now be 1/2 cosine A plus B. So now you can see how you can rewrite things. Cosine A minus B. So if the Webber-Sine problem says rewrite this as a sum, you just figure out the A and B and substitute them in, multiply by 1/2. That's all you do. The arithmetic of this is simple. It's just the beauty, the elegance is that we have this at all. So here we go. So these you have to put on a note card and become familiar with doing these types of exercises to derive them. Otherwise, they will not make any sense to you. Just to say, learn this is no good. That's rote memorization, which is absolutely useless. Now for 4, what we can do, if we want to absorb the cosine, here I've got rid of it. If we want to absorb the cosine, let's just say 4 minus 3. So we'll say subtract 3 from 4 to get the minus minus. So that's going to give us 2 copies of the sine. So we get 2 sine A, sine B. The cosines absorb, and we have the cosine A minus B minus cosine A plus B. Now divide by 2. So the product of the sines with possibly different arguments. say sine of 2x times sine of 4x maybe, is 1/2 cosine A minus B minus cosine A plus B. So though these formulas seem a little bit silly right now, they won't be silly when you see them in physics and when you see them in the calculus sequence. So again, WebAssign will just help you get used to using these. So when you start using these to do antiderivatives, indefinite integrals, or definite integrals, you'll be very happy that you know of these because they're going to cut down your work considerably. But then, of course, trig identities are like log identities. They can make things look really different. So again, if we want the product of two sine terms, we can write them as a sum, quasi-sum, the difference of two cosine terms. Again, the product of two cosine terms here written as the sum of two cosine terms here, sine, here, sine. Now, what's left? All we want to do is transform these into sum to product. Those will also be used in calculus, but in different ways. Basically, when you're doing continuity and differentiability arguments. So let's go ahead and look at those. Again, these are going to get more use than the sum to product, but I want you to see how we actually derive them. And it's real simple. Now, the idea with this example is that what you want to do is make the arguments of the sums simple. So here's what I'm going to do. Let's just write this as sum to product, sum to product. Less useful, but still useful. Certainly useful in real analysis. So here's what we're going to do. We just want to isolate this side and set it equal to this to multiply by 2. But we want this argument to be simpler. So we're going to let alpha be A plus B and beta be A minus B. So we do a change of variable. This is standard. Let alpha equal A plus B and beta, my two favorite, well, theta is probably my favorite. These are my second favorites. They're easy to write. Nice Greek letters. Now, why is this any good? Well, here's the kicker. Equivalently, A is equal to the average of alpha and beta. If you add alpha and beta, you get 2A. The B's absorbed, divide by 2, you have A. And B is just the difference between alpha and beta divided by 2. So this is a common change of variable. Now you make this easy and make this more complicated. So let's fill it in. So now we use the product to sum to get the sum to product. So we're being lazy, very, very lazy. So number 1. So now we have what? Sine alpha plus sine beta multiply by 2. That gives us 2 sine alpha plus beta divided by 2 cosine alpha minus beta divided by 2. You're thinking, how simple is that? And not as useful, but now we just make it user-friendly. So now, you might have sine of x plus sine of y, and then you have x plus y over 2, x minus y over 2 times 2. You're done. You're a genius. It's like, man, these make you look really smart. It's like, wow, look at this. Look what we can do. Okay, now go to the next one. Apply the change of variable. I'm demystifying these identities because they're not difficult if you know how they're set up. So now do the same here. We're going to have sine of alpha minus sine of beta. Multiply by 2, get the 2, and then cosine A, cosine alpha plus beta over 2, sine alpha minus beta over 2. There we go, we're done. Use alpha and beta. Using these tend to run together. When I teach Cal 3, I use U's and the Greek news so they don't look alike, but I've decided to use alphas and betas for this. Okay, well, say now we've got sums and differences of sine terms. Let's do the cosine terms. So now we'll have cosine alpha plus cosine beta, cosine alpha plus cosine beta, multiply by 2, cosine alpha plus beta over 2, that's A, and cosine alpha minus beta, that's B over 2. So we're like, when you look at these, notice the sine sums have the sine and the cosine. The cosines only have the cosines, and the sines and the difference of the cosines will only have the sines. So they're not as simple to remember. So what I will tell you, and I'll summarize this at the end. Let's do the very last one. Do the same song and dance. So here we're going to have, we're now look, we've got the beta there. So this is backwards. So we have cosine beta minus cosine alpha multiplied by 2. So we get 2 sine alpha plus beta over 2. And then we have sine alpha minus beta over 2. Now, the thing is, in the literature, it is preferred that the alpha term comes first. So what happens is that they multiply 4 by a negative number, -1, to reverse things. So multiply the whole equation by -1. So we get cosine, this is just standard, cosine alpha minus cosine beta equals the negative of sine alpha plus beta over 2 sine alpha minus beta over 2. So now, if we, just box them. So we have sine alpha, sine beta, same thing. So you're thinking these are all kind of interconnected, but the one that we focus on is this one. Even though the first one I've written here is equivalent to it, if you look in your identity tables for the book, they always have this one written with the cosine alpha term first with the negative here. So this is not how it's normally written. You just get everything with the negative. So these are demystified, but why are they so simple? Well, let's just kind of recap what we did. And I'll show this back up, so make sure everybody has this down. So I'll put this back up. We started with these, and then did some computations, and then got the double angle. We did the power reducing. We did the half angle, and we're thinking, okay, isn't that enough? Well, after we worked through that, we're thinking, okay, well, we need some more calculus identities, especially when we hit Cal 1 and Cal 2. So we're interested in the product to sum and then sum to product. But notice, if you know the addition and subtraction, or the sum and the difference formulas, going here, 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 and here, very simple. So these are really all you need to know, and you could easily derive all of these using these 4. So we add the 2 to absorb this term, and we get that, and then you're thinking this is redundant to flip this around, but that's fine, that's usually included. And then we want to absorb the sine term, so we add them. Then we want to absorb the cosine term, so we subtract them to get these formulas. So again, product to sum. Right now, it's like, just looks like just a bunch of gibberish, but very useful, very useful. And the WebAssign will give you practice with these. And then en route to here, we say, okay, let's make a change of variable so we can replace a plus b with a single argument and a minus b with a single argument, namely alpha and beta. And then we just simply take the last identities and flip them. We just solve for the sums, multiply everything by 2 to get rid of the 1/2. So all of these identities are equivalent because we get the identities from the previous identities. And the equivalence is easy because you saw how simple it was to go between them. So I don't want you to feel like you have to memorize the product of sum and the sum to product. I want you to know them. I want you to know them and understand them. And if you have them on a note card, fine. If not, you can easily derive them because you know these. These you should commit to memory because they come up so often, especially in physics, that you should have them committed to memory because you know them and you should be able to derive them the way I've done in class. The only way that you become efficient at the use of identities is knowing the arithmetic of the unit circle and knowing the arithmetic of the inverse trig functions. That really sets you up with all of this to solve equations with some degree of confidence. So remember, identities are not necessarily ones that you use all the time. You won't find as much use for these. You'll find more use for these. Of course, this is important because it gives you this. We will find that we have some use for the half angle. We will find that we have some use for the power reducing. Lots of use for the power reducing. We will find many uses for the double angle. So this is just basically a snapshot of all the different kinds of identities that you're going to see when you take your STEM math, more STEM math, and your STEM classes in computer science and physics and engineering. So what we want to do on Thursday is look at a couple of examples with these and then take these into solving equations using all of our arithmetic of the unit circle and Professor Ron's lemma. So again, we end with a bang in this class. So after we finish this, we'll do conic sections and then we'll do sequences and series and induction and the binomial theorem. So no rest for the weary, but that's okay. It's good to end on a high point. So enjoy the warm weather. Professor Ron is hoping that it gets a little bit cooler again. I was enjoying the early morning runs with the cool weather, but I'll take whatever. Thank you for your attendance today, ladies and gentlemen. And if I don't see you at the conference hours, I'll see you next time on Thursday. Bye, everyone.